Welcome back. In this lecture, we will see the derivation of logarithmic mean temperature difference, LMTD. It is called as logarithmic mean temperature difference. So we will find an expression for this LMTD in the parallel flow and counterflow configurations. And the temperature distribution of the hot fluid and the cold fluid along the length of your parallel flow heat exchanger is shown in this particular diagram. And you can see that this TH1 is the inlet temperature of the hot fluid, and it gets reduced to TH2 on the outlet. Similarly, a cold fluid enters at TC1 and it leaves the heat exchanger at TC2 with an increased temperature. Okay, and this difference in the inlet, TH1 minus TC1 or THI minus TCI, that is given by theta1. And you can see that the same way on the exit or at the exit, your THO minus TCO, that is going to be theta2. So in short, this theta is your temperature difference, which is the temperature of the hot fluid minus temperature of the cold fluid. Okay. So now in this entire heat exchanger, let us consider this small region of space with an elemental area, so that is the element that we are considering, and the area for this particular element, let's call that as dA. So dA is the elemental area, and for that elemental area, we are considering the temperature with which the hot fluid enters, that is going to be THI, and the corresponding THO is going to be over here. So the difference between this TH I and THO over here. So this is going to be THI, and this is going to be your THO. So the difference between these two, that is what is given as DTH. And similarly, the difference in the temperatures at the exit and inlet, that is going to give you the DTC. And the heat transfer rate within this elemental area, we are going to call it as DQ. Okay. So with this in mind, let's write the equations right now. So your dQ in the elemental area, that is going to be equal to U times dA TH minus TC. Okay. So it is supposed to be U times dA delta T. So that your U is called as the overall heat transfer coefficient. So this is similar to what you see in your convective heat transfer, where you have Q is equal to HA delta T. So in place of H, we have got U, and in place of A, you have got the elemental area dA, and TH minus TC is your delta T. Okay. And the same dQ can be written as minus m dot H CPH into THO minus THI. It is conventional that we write this delta T as the final temperature minus initial temperature. So here the final temperature THO is lesser than the initial temperature THI. And to compensate for that, we are introducing a minus sign before this. And if you look at the cold fluid, that is going to be m dot C CPC TCO minus TCI. And we know that this product of the mass flow rate multiplied by the specific heat can be written as capital CH, and mass flow rate of the cold fluid multiplied by CPC can be written as capital CC. The CH and CC are called as capacitance rates. Okay. And capacitance rate CH is going to be capacitance rate of the hot fluid, and CC is going to be capacitance rate of the cold fluid. And so these guys can be written as minus CH times. So THO minus THI, that can be written as DTH. And this guy can be written as CC times dTc, the change in the temperature of the whole fluid. Okay. And so I can define the CH as minus dq divided by dTh, or let me write it the other way around. So your dTh is minus dq divided by CH, and dTc is going to be dq divided by Cc. Okay. And so now the temperature difference, dTh minus dTc, or which can be written as d of Th minus Tc. D of Th minus Tc is going to give you dTh minus dTc. And we know that Th minus Tc is going to be your theta. So it is d theta equal to minus of minus dq times 1 by capital CH plus 1 by capital Cc. Okay. Now in place of dq, we have already defined dq as u dA times Th minus Tc. And so this dq, this expression for dq over here, this expression for dq over here can be substituted in this particular equation. So that makes dTh minus dTc is going to be equal to, which is d theta. So let's keep it as d theta. That is going to be equal to minus u dA times 1 by CH plus 1 by Cc, and there is this Th minus Tc. And remember, this Th minus Tc can be written as theta. So this can be replaced with theta. So your left-hand side, it becomes d theta by theta is equal to minus u times dA multiplied by 1 by capital CH plus 1 by capital Cc. The reason I mentioned this as capital CH and capital Cc every single time is to ensure that this guy is the capacitance rate and not your specific heat. Okay. Now you have got a differential form of equation on both sides, and this can be integrated on both sides as well. So when we do that, we are going to have ln theta, and that is between the limits 1 and 2, which is going to be equal to, whereas in this case, this is going to give you, so u is a constant with reference to A, and 1 by CH and plus 1 by CC. This is also going to be a constant with reference to dA. So when you integrate dA, you're going to get A, and area varies from 0 to maximum area A. So that is going to give you ln theta 2 minus ln theta 1 that is going to be equal to minus u times A 1 by CH plus 1 by CC. Okay. So this guy can be written as ln of theta 2 by theta 1. That is going to be equal to minus UA times 1 by CH, capital CH, plus 1 by capital CC. Okay. So now what we will do is we will try to write an expression. This CH, let's substitute with something else. What we have already seen is your Q is equal to CH times TH1 minus TH2, and this is also equal to CC times TC2 minus TC1. So your CH can be written as Q by TH1 minus TH2, and your CC can be written as Q by TC2 minus TC1. Your 1 by CH is therefore going to be TH1 minus TH2 divided by Q, and 1 by CC is going to be TC2 minus TC1 divided by Q. So your 1 by CH plus 1 by CC is going to be TH1 minus TH2 minus TC2 minus TC1 whole divided by Q, because Q is common in both the cases. And this can be rearranged as TH1 minus TC1 minus TH2 minus TC2 whole divided by Q. And we already have got this expression ln θ2 by θ1, that is going to be equal to minus UA times TH1 minus TC1 minus TH2 minus TC2 whole divided by Q. We can absorb the minus sign inside, and you would get UA by Q times TH2 minus TC2 minus TH1 minus TC1. So that gives us UA, or we will call this as Q by UA equal to θ2 minus θ1 divided by ln θ2 by θ1. Okay. Or this can be written as Q equal to UA theta M, or UA times delta T ln. So it is this theta M or delta T ln which gives you the expression TH2 minus TC2 minus TH1 minus TC1 whole divided by ln of TH2 minus TC2 divided by TH1 minus TC. So this is the expression that we have for the LMTD of parallel flow heat exchanger. Thank you.